Hello and welcome to the section of the Physics 3 tutor. Here we begin to discuss something that everybody's heard of, and that is the topic of the magnetic field and magnetic forces and how magnets and magnetic fields interact. And I can tell you, as a kid, playing with magnets, for me personally, was something that got me interested in science at a really, really young age. And I think all of us can agree that there's just something magical about magnets. You have a piece of metal, more or less here, another piece of metal here. You put them together, they attract. If you flip it over, they repel. They can pick up certain metals and pull them and make them stick to the magnet and attract the magnet with the magnetic force. Some metals, it works fine. Other metals, they're not magnetic at all. So it's just something about that when you're a kid playing with that just for me, tickled the imagination. So here we're going to begin to talk about that from a nuts and bolts fundamental level. Now I'll tell you, the theory of how magnets work and how magnets repel and attract objects is pretty well defined. However, when you learn this stuff in physics, you're going to reach a point where if you keep asking why and why and why and why deeper and deeper and deeper, you're going to get to a point beyond the scope of this class, right? So in other words, I can tell you what the magnetic field is. I can tell you how it attracts and repels metal, right? But then you might ask, well, why does it work that way? Well, then you have to start digging even deeper than a basic physics course. You have to start talking about quantum mechanics and things that are just so far removed from our everyday experience that they become very, very different and very complicated. So never stop asking questions. And we're going to learn a lot about this stuff, but I guess what I'm trying to tell you is that at the end of the lesson, you still might scratch your head and say, well, why does it work that way? Well, that's sometimes really difficult to answer that question in the scope of a class. We're going to look at the how. The why does it work that way is really a deeper question, all right? So what we're going to do is I'm going to compare and contrast what we've learned, some fundamental things we've learned about the electric field first, because we've talked a lot about the electric field. Then we're going to talk about the magnetic field because I want to begin to make the connection in your brain that the electric field and the magnetic field are pretty much intertwined. In fact, they actually come together and form an electromagnetic wave that you'll talk about later. That's a light wave. That's a microwave. That's a gamma ray, whatever. They're all electromagnetic waves. So electricity and magnetism, they go hand in hand. And by listing the properties of electric field and magnetic field, I think you'll be able to make that connection. So even without any math, you'll be able to say, wow, that's really neat that nature works that way. All right, so let's first, before we talk about magnetic fields, let's recall for the electric field. We represent that by E bar, E vector, however you want to think about it. And these are things that you all should know. There should be really no surprises here. The first one, and we'll talk about these in general, they're very, very simple overview things. The electric field is generated by charges. Right? We talked about that a long time ago. We said, hey, if we stick a proton in empty space or an electron in empty space, then surrounding that guy, we're going to say, happens to be an electric field. It's invisible, can't touch it, can't taste it, but it's there. We know it's there because if we take other charged particles and put them in there, in the field will then act on it and create a Coulomb force, a force that then pushes, the object. That's basically how you observe an electric field when you think about it. But when we talk about these electric fields, we basically say that we stick a charge in space. The charge does not have to be moving, does not have to be special. It just has to have some charge. And then out forth from that, the guy springs an electric field. All right. Another property that we know, that's a very simple, basic thing. The electric field, for lack of a better word, goes outward forever from the charge. I'm going to put charge Q here, from charge Q. What do I mean by that? I'm just basically trying to say in words what we've done all along. If we draw a proton here, then typically the way we did it was the electric field kind of radiates in all directions. Stronger as you get closer, weaker as you get farther away. So I'm drawing my arrows a little bit shorter as I get a little bit farther away, right? So it goes all the way around. And if you look at the equation of the electric field and how it falls off, classically anyway, you'll see that you can take the radius, the distance from the charge off to infinity, and you'll still have a teeny tiny electric field out there. So you stick a charge here, the electric field bleeds off, but really you can go as far as you want. There'll still be a tiny electric field from that source, right? And finally, what we've already said in words, I'm only going to do three things here, three important topics. The third one is if a charge, let me write it like this. If a charge Q is placed inside the electric field that we're labeling E, a Coulomb, which we talk a lot about this, force, pushes Q along the electric field lines. All right, it's a lot of words. Really, I just want to have everything written down. What it's trying to basically say is, look, you have some electric field here. It's generated by something. In this case, we say, hey, it's generated by a charge we put in space. Now, if I take a tiny electron and I stick it right there and let go, then this electric field is going to push this electron. And the reason it pushes it is because a Coulomb force pops up. We calculated lots of problems before with the Coulomb force. And the direction that this Coulomb force is going to push is going to be along the field lines. If I place the charge here, it's going to push it this way. If I put the charge here, it's going to push it this way. If I put the charge here, it's going to push it this way. So we've talked about that. You're going to find in a second that magnetic field actually behaves completely differently in lots of different ways, but yet the duality is still there, and that's really one reason why it's so important. All right, so let's go and talk about the magnetic field. So we call this, for the magnetic field, right? And we talk about an electric field E. The magnetic field, we talk about magnetic field B. You might think, oh, magnetic field should be M. Well, it's a lot of history and why it's named this way, but the field is called B, right? There's a bar on top because it's a vector field. There's a direction to the magnetic field. That doesn't surprise you. If you turn magnets over, I mean, it behaves differently, so there's got to be some kind of direction to it there. So that's why it's labeled a vector. Now let me switch colors just to sort of differentiate that. I'm going to try to draw some parallels to what we talked about a minute ago. The magnetic field B is generated by, and I'll explain this in a second, moving, underline it, charges. I'll even put an exclamation point. That's pretty cool. There are no identified quote magnetic charges in nature. What do I mean by all this stuff? You know, you might think that if an electric field is generated by an electric charge that you put here, and then, whoops, electric field just pops up, this magic thing, we have a charge, then you might think, since there normally is symmetry in nature, that there would be a magnetic charge in nature. And we would pull this magnetic charge. Maybe magnets were made of magnetic charges. That's what people thought for a long time, right? And you take a magnetic charge and you stick it in space and poof, out pops a magnetic field from the magnetic charge, just like an electric field, poof, pops out from an electric charge. Nature is not like that. In fact, for a long time, people did think magnets were made out of this very special magnetic charge material that, you know, was special, and you mined it out of the ground, and then it just springs forth a magnetic field. It doesn't work that way. Magnetic fields are only generated by regular old electric charges like electrons and protons, but they have to be moving. I'm going to say that 2 more times because it's so important. Magnetic fields are only generated by regular old charges like protons, electrons, ions, whatever, regular electric charges that are in motion, right? 3rd time. Magnetic field's generated by charges in motion, right? I'm going to get into a lot of examples, but just to show you, if I build a circuit right here, draw a circuit, put a battery, wire, coming back to the other side of the battery, there's an electric current moving in that wire. That means charges are moving. If you get a magnetic field meter and you hold it next to the wire, then you will read a magnetic field. If you switch the battery off or open the circuit, right, so no charge is moving anymore, then there's no magnetic field. The magnetic field just stops. It only springs up when charges are in motion. And people have scratched their heads for many, many years trying to really understand at a detailed fundamental level, why does it spring up? Why is it that when electrons move or protons move, a magnetic field pops up? Those are very deep questions, really beyond the scope of the class, but that is a fact, all right? So there are no magnetic charges in nature. You can't go mine a magnetic charge. Magnetic fields are generated by moving charges. Now I'm going to get a little bit ahead of myself for a second, because I know the fundamental question you're thinking right now is, well, if magnetic fields are only generated by charges that are in motion, how do magnets work? How do the fridge magnet, why does it work? I don't have it hooked up to a battery. I'm certainly not making a charge move around. Well, the theory is that if you could look at a magnet, a permanent magnet, on a microscopic level, at an atomic level, right, go all the way into the atom, then what you find for these permanent magnets, these special materials, have atoms that are all lined up in a very special way, right? And all of those electrons are orbiting all of those atoms, but they're all lined up. I'm not even going to bother drawing a picture, because if I try to draw it, it'll just be kind of hokey. Just imagine billions of atoms in this material. And normally atoms are kind of randomly have their electrons orbiting in certain ways. But in a magnetic material, the atoms are all aligned in a special way so that the orbits of the electrons, for lack of a better word, they kind of line up. And when they do that, the magnetic force fields, the magnetic fields, can then line up and basically come out of the material. That's why permanent magnets work, even though there's no battery connected to it or anything else. The magnetic field is individually generated by all the motions of those electrons whizzing around the nucleus, but they're all lined up. That's why you can measure the field outside of the object. In a regular material like this plastic pen, there's billions and billions and billions of electrons zooming around their atoms, but they're all randomly oriented. Some are pointing this way, some are pointing this way, some are pointing this way, some are pointing this way. So yeah, there's tiny little magnetic fields in here, but they all cancel out because they're all pointing in random directions. But in a magnetic material, you can force them to line up, right? You can force them to line up. The other thing is, the Earth itself, the entire planet, has magnetic field, right? We know this because we can have a North Pole and a South Pole. We use compasses to track the North Pole, right? How does that work? Well, the theory, again, this is all theory. Nobody's traveled to the core of the Earth, but the theory is, if you look inside of the Earth, you got very hot magma, right? And you've got that hot magma, which has charges in there, and it's basically circulating still from the formation of the Earth, basically. And the Earth is spinning and everything else, so there's lots of things going on. But basically, you have this circulation of this very hot magma that carries charge inside of the Earth, and from that springs forth magnetic field. Very good thing. We really need the magnetic field on Earth to protect us from the sun's harmful stuff. So, we haven't really written much, but we've talked a lot. Magnetic fields are generated by moving charges. They always are. So anytime you have a circuit, anytime you have anything with a charge moving, you have a magnetic field. All right, let's talk about number 2. Magnetic field lines always form closed loops. They always form closed loops. And what do I mean by that? We've all seen this picture. But let's say you have a bar magnet, right? So here's a bar magnet. Here's what we call the North Pole. Here's what we call the South Pole. The labeling of the poles really doesn't make any difference. They're just different from one another because you know that when you flip it around, they attract and repel, right? So what this means is, if you go back to the electric field, if you stick the source of the electric field there, the field radiates and goes everywhere, right? It basically just goes in all directions. Here, if you stick the source, which is like this bar magnet in this case, of this magnetic field, then the field lines form closed loops. You'll have something coming around like this, an arrow to denote the direction of the field, right? So you have something like this happening. No matter how far away you go from this magnet, you've basically got a closed loop. And of course it goes on the other side as well. And I know you've all seen pictures of this, so I'm not going to spend too much time. But this is more or less what it looks like. I'm drawing arrows because this is a vector field. And so the same analogies apply to the electric field. The closer the field lines are, in reality it would look more like this, really close. You would have really close to the magnet, you have lots of closely spaced lines. As you get farther out, like maybe way out here, it goes way out, right? So the farther spacing you have between your field lines, the weaker your field. And the closer spaced your field lines, the stronger your field. That part is really the same between both. In general, any vector field, whenever you have the closer spaced lines, it's stronger. When you have everything spaced out, it's weaker. But the huge difference is that with this guy, it doesn't just go in all directions like that and just get smaller and smaller and smaller. It does go in all directions, but the field lines themselves are closed loops, and that's always the case. For a bar magnet, these are the closed loops. I mentioned before a wire. Pretend this is a wire in an electric circuit. Electricity is flowing through this wire. I told you a minute ago, there's a magnetic field. Well, that magnetic field here is actually concentric circles around the wire. If you could actually put on goggles and see the magnetic field everywhere around a wire, you would see circles around the wire everywhere. It'd be going round, 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 little bitty circles like this. And they would all be closed loops because magnetic fields always form closed loops. All right, so we talked about the closer space lines give you higher strength fields, and the farther spaced you have weaker. Now you can do this experiment. If you get a bar magnet and a clear transparent paper and sprinkle the iron filings there, shake it a little bit, then you'll see the iron clumping where the field is stronger, and you'll see it spreading out where it's weaker. That kind of demonstrates that. We talked about that. We talked about the permanent magnet field really comes from the circulation of the electrons inside the magnet, and they're basically aligned, and that's what allows that magnetic field to kind of add up, so to speak, and come out of the device. We talked about the magnetic field of Earth comes from the circulation, the movement of the material basically inside the Earth, and we talked about a straight wire even has a magnetic field. So these things are fundamental, right? These things are fundamental. An electric field is basically generated by discrete charges we can find in nature. The electric field emanates outward and comes straight out from the charge, and it goes in all directions. And thirdly, if we put a charge in this field, it will have a force that'll pop up and go in the direction of the field line. It'll push it along the field line. Magnetic field's a little bit different. It's only generated by charges that are in motion, right? And the magnetic field lines only form the closed loops. Those things are probably the top level things that really separate electric fields and magnetic fields from one another. And here in a few minutes, we're going to discuss kind of the other half of it. So far, I've talked to you about how do magnetic fields form, right? That's what I've mostly talked to you about. But we haven't talked about what forces do a magnetic field exert on other objects, right? So that's the other half of the problems. That's what we're going to talk about here in just a minute.